Hello, good afternoon, everyone. Good evening. Okay, so let me get started with today's one. Okay, so I can see there's quite a lot of questions on the Slido. Okay, regarding this topic. Okay, yeah. At first glance, it does take a while to try to make sense of how this whole thing works. Okay, pipelining and all this hazard detection and control and so on. Okay, so I'll try to explain it again clearly over here. All right, hopefully by the end of this session is a bit better. All right, so I'll go straight to the quiz questions. All right, and I think from there we can when we go through the Slido questions, we're also going to go back to the lecture slides. Okay, so let me get started here. Okay, so as before, if anything happens with the connection or the Zoom call, just stay on. Okay, I'll come back in. Okay, so let's look at the question. So the first question is there are 6 stages in executing an instruction, and there are 10 instructions in a program. So each stage takes 1 clock cycle to execute. Okay, how many clock cycles would we need, okay, to have to complete this program? Okay, so this is fairly straightforward, correct? So all you need to do is you have 6 stages. Okay, 6 stages and 10 instructions. So the formula is basically the number of instructions plus n minus 1, which will be 10 plus 6 minus 1, which will be 15. All right, so again, this is an ideal pipeline. That means there are no hazards to deal with, so there is no stall in the execution flow. Okay, so we will come to stall and all this in a while. Okay, pipeline registers can store which of the following? PC plus 4, sign extended. All right, so let's look back at the picture. Okay, the pipeline. Let me take out one of the pictures here. Okay, so when you look at this picture, okay, this is with the pipelining. Okay, what we observe? We observe that there are registers, correct, to hold information for us when we go from one stage to the next stage, correct. And if you look at each stage, okay, the registers, the size is actually not consistent. Okay, the size is actually different. All right, so if you look at, for example, the first stage, okay, this IFID stage over here, what is the information that I need to store here? Okay, so from this design, you can see that I need to store one instruction, which is 32 bits. All right, then I need to store this PC plus 4 value, which is also pointing to an address which is 32 bit. Correct. So if I just look at this IFID sort of register bank, I will need a total of 2 32-bit registers to store this in the pipeline. Correct. But if I go to the next stage, okay, go to the next stage, you see that I have a lot more information to store. Correct, because each of this data that I read is 32-bit. When I sign extend, this is 32-bit. All right, then I have another 5-bit here, okay, for the register destination. Again, another 5-bit here as well. Correct. Then I also have my PC plus 4, which is another 32-bit. Plus, I have my control signals over here. All right. So in terms of size, you can see that the amount of information that I saw in each stage is different. Okay, so I need different sort of sizes of register banks to hold information for me while my instruction is propagating through the pipeline. Okay, so coming back to the question, you can see that I will need, okay, registers for all these stages. Correct. So PC plus 4, you need it in the first stage. Correct, the IFID stage. All right. Assign extended immediate operand is where? Is over here. Okay, that I will add to the IDIX stage. Register values are also the IDIX stage. Control signals are in IDIX, EXMEM, MEM, write back, and so on. Okay, the register number, okay, RR1, RR2, and write. Okay, this will be stored where is part of the instruction. All right, so that is in your IFID register. Your ALU output, okay, ALU output is stored in your EXMEM register bank. Okay, your 32-bit instruction is in your IFID bank. Okay, so basically all your information here, you need to store it somewhere. All right, as your instruction goes through from one stage to the next stage and so on. Okay, so all of them will be stored in the pipeline registers. Okay, each of the pipeline registers contain multiple registers. Okay, so this is what I talked about just now. So you contain multiple registers and it's not the same, correct? As we just saw, in each stage you have different amount of information to store. Okay, so but you definitely need a lot of registers to store this information. So you have multiple registers, each 32-bit. Okay, to store all this information for us. Okay, so it's true. And the MIPS processor that we discussed in this course can execute at most 4 instructions in ideal pipeline. Not true, correct? Because in an ideal pipeline basically means if there are no, if the sequence of instructions is such that there is no dependency, correct, that requires any stalling and so on, then you can continue and execute as many instructions as possible. Okay, so this is false. Okay. Okay, so the question is it possible for a pipeline register to only require non-mod 32 bits, a pipeline that requires, okay, so yes, you store information that is not necessarily 32 bits, all right, but again, I would say this is what do you call, dependent on the application or the sort of hardware design. Okay, we know that we need to move information around, correct, and to move information around, we store this data in registers, correct, and how the hardware is configured, it is not to say it has to be always 32-bit. Okay, so for example, if I look at control signals, I may not have 32 control signals, correct? I may only have maybe 3 or 4 or 5 control signals that I go from stage A to stage B and so on. Okay, which means that I can say that I set aside a certain number of registers just for that, or I can say that I will bank together all these individual bits and then create one 32-bit register. Okay, and then extract out the individual bits from there. So for example, those that are not 32 bits, okay, I can say that, for example, this one over here, this one over here, I can group them over here and say, okay, this 5 bits come here, this 5 bits come here, this 3 bits come here, and so on. And then that will be one register that will hold all this control signal plus all this other signal that is not coming up to 32-bit, and that will be one register. Okay, that is one possible implementation. Okay, so you may have to move data around that is not 32-bit, but you can always pack it together to make it 32-bit. Okay, or into a 32-bit register, but not necessarily using all the 32 bits. All right. Again, comes back to the idea that a register is not a data type. Correct. A register is just a place to store information, which means that when I have a 32-bit register, doesn't mean that I need to use all 32 bits. I can only use a part of the 32 bits to hold some information that I need. Okay, so let's move on to the next question. So here with okay, so what independence is, you can see that instructions has some examine the dependencies, okay, between subsequent instructions. So let's look at them one by one. So the first instruction over here, okay, give me a laptop is not really responding right now. Okay, can you hear me clearly? Okay, thank you. I need to get a new laptop, I think. Okay, so sorry about that. Let me continue. Yeah, my laptop always goes into this sudden high fan speed mode and it just freezes, and having a hard time trying to deal with it. Okay, so let's continue. So here we have a sequence of these instructions. Okay, so let me blow up these instructions here. Okay, so if you look at the first instruction, we are reading from T1, okay, and we are writing to T1 in the next instruction. Okay, so in this case, it is a write after a read. Okay, right after a read between the B and A. So right after a read, there is no issue. Okay, right after a read, there is no issue because you have already read the original value and you're using it, and then you're updating it in the subsequent instruction B. So that is fine. Okay. Now in B, you are updating T1, all right, and in C, you are reading from T1. Okay, so if you look at this, in B, you are updating T1, okay, which means you are writing to it. And in C, you are reading from T1 to perform an operation. So this is actually a raw instruction, read after write for register T1. Okay. Now between C and D, you see that both C and D are updating T6. Okay, so that is fine because here you are updating T6, so it's right after write. Okay, so that is for T6. Okay, now the next one here is between D and E is read after write. Correct, because here I have T6. So it is a read after write over here. Okay, for the last one, you are updating T6. Okay, so there is no issue over here. Okay, it's a right. So it's right after read. Yeah, correct. Okay, you are using T6 in the early instruction, you're reading from it. Okay, and in the instruction T6 when you are writing to register, so it's right. So it actually is a read after read, not after read after read. Sorry about this. My laptop is again giving me issues. Okay, so the dependencies, okay, are what you see here. Okay, so let's go on to question 6 on forwarding. Okay, so we have a sequence of instructions and we are asked to look at the cases where there will be or how it will execute if I have forwarding and if I don't have forwarding. Okay, so let's do so this is, let me change this. So this is no forwarding and this is forwarding. So let me add on first. Okay, so there's a question from B to C. Can it be both write after read and read after write? Yeah, I mean, because we have both two registers that are used in both cases. So for T1, it is read after write. Okay, for T6, it is write after read. Okay, so this is write after read for T6. Okay, for C and D, also the same thing because you have T2 as well. Okay, so in so you also have T6 used here. All right, T6 used. So in this case, it is read after write also. Okay, for T6 because you are using T6 as the input at the same time as the output. Yeah, so it's correct. So there are other data dependencies as well. Okay, so coming back to this, okay, so we will look at the case of no forwarding first. So in this first case, first instruction is fetched. Okay, so for the second instruction, we are updating T1. All right, so it is write after read, so there is no dependency there. So I will be able to execute fully. Okay, so it will be fetch, decode, execute, memory, and write back. Okay, now for the third instruction, we can see that there is a dependency in T1. All right, so T1 will only be completed in the memory cycle, correct? T1 will only be updated when I reach the mem stage over here. Okay, because the load word instruction. So only after I fetch the data from the memory, I know what is the value in. Sorry, this is no forwarding. So no forwarding means only when the write back is completed, the T1 is updated. Correct. So in that case, when I fetch the next instruction, okay, I cannot go on to decode stage. Decode means I read from the register, right? But I cannot decode yet because I don't need it after the file values have been updated. So I need to stall. Okay, so the fetch I stall for 2 cycles, then I decode, then I execute, okay, then memory and write back. Okay, now since okay, so if you remember, we can do a write back and read at the same time, okay, because the write back will be in the first half of the clock cycle and the read will be the second half of the clock cycle. Okay, so in clock cycle 6, we are accessing the register file in the same clock cycle. Only thing in the first half we do a write, which is from instruction B, and in the second half we do a read, which is from instruction C. Okay, now after I complete instruction C, all right, again, since I have stalled, I can only fetch the next instruction here, okay, in cycle 6. All right, and in cycle 6, when I fetch the instruction, there is also a dependency because here I update T6. All right, then I need T6 over here. All right, which means I have a dependency, okay, for the earlier instruction to complete. So I need to again wait until the write back. So I need to stall, then decode, execute, memory, and write back. Okay, so the next instruction can only be fetched over here. Okay, the end. And again, I see that I have another dependency here. T6 is updated in instruction D and T6 is needed in instruction E. So again, I have to stall, then decode, execute, memory, and write back. And finally, my last instruction, there is no issue because it is right after a read for T6. Okay, so I just have to fetch here and then I can continue from there on. Okay, so total I will take 16 clock cycles. Okay, next is with forwarding. All right, so with forwarding, let's see what happens. So we can see the first instruction is already there for us. So the second instruction, we can also go ahead and execute as per normal: fetch, decode, execute, memory, write back. Okay, now for the third instruction, dependency in T1. Okay, so when I fetch, okay, so I need this question. We were looking at the forwarding, okay, option. So the instruction C will fetch, decode. All right. So we know that the earlier instruction is a memory instruction, which means that the data is available after I complete the mem stage. Okay, which means I have to do a stall over here. After I do a stall, then what will happen is I need to the data from the mem stage to the next. I need to trigger. Okay, so when I forward it, the exe stage will come here. All right, and then I will do the memory and write back. Okay, so I can execute once the earlier instruction has completed the memory stage. Okay, so similarly, when the fourth instruction comes, I will fetch here. Okay, since I already stalled, okay, in cycle 5, I will have a stall here. So the decode will come here. Now, again, the same thing. Okay, you can see that there is a dependency here, T6 and T6. All right, and in this case, the earlier instruction is R type instruction. So it's R type instruction means I can forward from the exe stage. So I can forward, okay, and then I can execute. Okay, memory and write back. Okay, for the next instruction, I can start in cycle 6. Okay, which will be fetch. Okay, decode. Okay, again the same thing. You will see that there is a dependency for the T6 and T6, which means that and the earlier instructions are from the EXE. So the EXE says forward. Okay, then I'll be able to execute here, then memory and okay, and then the final instruction I can execute, and there is no forwarding and dependency here. Okay, wait, let me look at the questions. Is there a difference between stalling at 5 or 6 for D, or does it not matter? Okay, so when your processor, when your instruction is stall, okay, it is stall means, okay, that means your earlier instructions are not passing through the pipeline. Okay, they're not passing through the pipeline. So it means that if I look at my earlier instruction here, see, I am stuck in the decode stage. So when I'm stuck in the decode stage means I'm occupying the registers, okay, in the decode stage, which means that I cannot have another instruction come in and occupy the decode stage. Correct. At any point of time, only one instruction can occupy one stage at a time. Okay, so it is not possible for the decode stage to come here. Why? Because the earlier instruction is still stuck in the decode stage. Okay, so there can only be one instruction in one stage of the pipeline at a time. So that is why you have to stop the instruction D in the fetch stage until the earlier instruction goes to the next stage. Then the decode stage is freed up, and then I can move on. I hope that answers that. Okay, for instruction number 4, is it possible? Yeah, so I think I answered all the questions. All right, so I think 3 of you had similar doubts. Okay, so you basically have to understand that instruction in one stage at a time. Okay, so if an earlier instruction is in a decode or execute stage, the next instruction cannot go into that stage until it is cleared. The earlier instruction is cleared. Okay, so let me go through this. So in this question, what we have is we have assumed branch taken, prediction strategy, and the actual is taken, and the branch decision is made in the memory stage. Okay, so let me draw the lines first. Okay, I just have to hope my laptop lasts till the end of the session. Okay, so this is 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so let's go through this. So the first instruction, no problem. So fetch, decode, execute, memory, write back. Now, for the second instruction, I will fetch. Okay, so there is a dependency because of S2. Okay, because of S2 being updated in the earlier instruction. Right, and we want to use S2 again in the branch comparison. Because I have a fetch. Okay. Okay. Now I can't move on to the execute stage because the branch computation is done in the ALU. Right. So the execute stage cannot complete until the memory stage is done for the early instruction. Okay, so I need to do a stall over here. Okay, so once I do a stall over here, then I can do a forwarding. We can do forwarding here. And I can do the execute stage here, followed by the memory and write back. Okay, and since we say that the branch is taken, okay, which means that the next instruction, okay, would be this instruction. Okay, so we always assume that the branch is taken. That means when I fetch this instruction, I will from here I will go straight to here. So this sub instruction will not be fetched from memory. So I would fetch it over here, fetch this instruction, and since this cycle is a store here, the code will come here. Okay, so this is a case where the branch prediction is that the branch is always taken, all right, and the branch is test is true. That means I will take the branch. Okay, so that is what happens here. For the BNE instruction, is it possible to stall right after the fetch stage? Okay, so right after the fetch stage, it will stall when it, memory stage. Okay. I'll show you one slide. Okay, I'll show you one slide that some user in this week. For it, in a logical sense, you can say that why don't I just stall it in the beginning, since I know that this is the instruction and so on. But all this hazard control mechanisms are all hardware triggered. Correct. That means in the hardware, we will actually have all these checks to know that this hazard is happening, and we will try to solve it in the hardware. Okay, so when we say solve it in the hardware, it all comes back to the many of the principles of the whole processor design. We want to reuse existing hardware as much as we can. So if we already have the ability to do forwarding from memory to memory, then it makes more sense to, if possible, just stall it in the execution stage or just before execution stage, so that when I go to the exe stage, the forwarding happens and the correct data is available. Okay. So I will show that in a while. Okay, so there's a question is that we need it is in line with the instruction we're executing, correct? So in our case, we know that we are executing this instruction, this L1 add instruction, so we leave the other line blank. Okay, so that is with the branch taken prediction. Now let's look at the branch taken, branch not taken prediction. Okay, so let's go through the first instruction will be fetch, decode, execute, memory, write back. Now for the next instruction, again we have the dependency for S2. So fetch, decode, correct, and then we will have to do a stall, okay, and then execute, and this is memory and write back. Now in this case, the prediction is branch is not taken. So if the branch is not taken, then we go on to the next instruction. I will go on to the next instruction, which means I will fetch this instruction here. Fetch. Okay, this is a stall. Then decode. Okay. Now, when I reach the exe stage, that is where my earlier instruction reaches the mem stage. All right, and okay, so it's in clock cycle 6 where we make the decision. Okay, decision to branch. So once we know that we are supposed to branch, that means this instruction should not be allowed to continue. Correct? Should not be allowed to continue. So we will flush, okay, this instruction. All right, and then in the next clock cycle, we will fetch the correct instruction, which is here. Okay, fetch, decode, okay, execute, memory, and write back. Okay, so in this example, basically what we are saying is by default, we assume that the branch is not taken. So we proceed on to the next instruction. But when we make the decision, all right, based on the values that the branch is supposed to be taken, then we will have to flush that instruction and fetch the correct instruction to be executed and continue from there. Okay, so why can't I start? All right, so what will happen is what I say is correct, okay, but I wanted to say that after I say this, which is by right, since L1 instruction is the next instruction after sub, we will actually fetch here and we will go through decode here. Okay, but okay, what is happening is because at this point here, I say I must flush. Okay, so at this point here, I say I must flush the pipeline. So when I say I flush, I have to clear all the stages, okay, in the pipeline before that. So which means that the fetch and decode that were actually fetched from the next instruction would also be cleared, and then I have to restart. Okay, flush, yeah, flush doesn't affect instructions before it. It's only the instructions that are after the current execution stage. I mean the current stages before in the pipeline. Okay, so this strategy, it in a sense doesn't improve the timeline much because our decision is still in the mem stage, correct? So if I want to improve it, then I have to use the early branch prediction by moving it to the decode stage. Then I would have saved 2 clock cycles. Okay, is that okay? Any other questions? Yeah, I mean, if there's a question on branch, definitely we will specify whether it is the default design or is it a early branch predictor. Okay, so if there is no information, you take it as by default the design as you see originally. Then if there is mentioned that it's an early branch detection, then we have moved it to the decode stage. Okay, so that is all the questions. All right, now let me go through. Okay, so before I go through the Slido questions, let me jump to one of the extra slides that I have to give you the idea of what this forwarding is all about. Okay, so this is from 2100 back in 2016 when I taught it. Okay, so we used to go into all this hardware detailed implementation. Okay, but I think we have taken it out already. Okay, but though it is not covered, I think I just want to show you so that you have an idea of what is forwarding. All right, and forwarding is actually not really forwarding, it is actually going back in time. All right. Okay, so if you look at the idea of forwarding, what is the idea of forwarding? We want to make data available from one of the later stages backwards to an earlier stage. Okay, but we call it forwarding in a sense that because the next instruction is in the earlier stage, so we're sort of bringing it forward for that instruction. Okay, so we call it forwarding, but we're actually moving it back, okay, in the pipeline to make it available earlier for the next instruction. Okay, so there are two types, okay, in a sense, where an instruction like this, okay, for example, where I am updating one register here, okay, and I need that register for the next instruction. And if you look back at your design, okay, I mean your MIPS instruction coding, this is your, let's assume this is your RD register, okay. Of course, you have immediate and all those other stuff, and okay, but I'm just going to show you one example. All right, so it's not to overcomplicate things. So assuming this is R-type instruction, so you know it is RS, RT, and RD. So my destination register is RD, and we know that if the next two instructions are like this, okay, that means the is either RS or RT. Okay, so I'm just going to show you this specific example, but in hardware, we will of course design the whole system, all right, to cater all the different solutions. Okay, now if this was the case, then we know that if in my earlier instruction, the output is supposed to be my RD register, and if that matches my RS register in the next instruction, then I do forwarding from this to this. And similarly, if my second instruction after that also depends on the same register, okay, and then I need to do another forwarding, but again, it could be RS, it could be RT. Okay, so that is the concept. Right? We understand this idea of forwarding based on this concept. Now, how will I implement this in the code? Okay, so in the code wise, okay, so let's look at the code wise. Okay, this is of course code as you see it, but again, like I said, this is another language altogether, in a sense that this will be what we call hardware description language, where we will generate hardware based on software. Okay, now if I look at this code, what do we understand? We can see that if my current EX memory instruction, that means my current instruction, which is in the EX memory stage, is performing a register write. Is performing a register write. That means I'm doing this. Correct. My current instruction is updating a register. Okay, it's updating a register. Then, okay, what I'm checking is if this register that I'm updating, okay, which is the RD register, is it the same as my RS register, which is currently in the EX stage? Okay, that means my second instruction and is in the EX stage, which is this stage over here. So you can see the logic. That means I'm saying that my earlier instruction, which is already finished the EX stage, that means it's the EX memory stage. Okay, if that register RD register, is it the same as my current instruction, which is in the IDEX, okay, register RS. That means in the instruction that has just finished the IDEX, that means the earlier pipeline registers. That is from here. From here is going to come into the next stage. Okay, so this is the third stage and this is the second stage. So is there a match there? Or the other condition is EX memory register RD, but is matching the IDEX in the register RT. Okay, so this is the case where the ALU input is from the previous instruction. Okay, from the previous instruction. Sorry. Okay, now when I do the forwarding, what is happening here is, again, this is not covered in the syllabus already, but I'm just showing you so that you can visualize what this forward just draw the line, just draw but actually what is happening is okay, so it's under forward. Okay, so here you can see under forward A is written as 10, forward B is 10. So where is this forward A and forward B? So coming back here, there are actually additional multiplexers that I now add to the input of the ALU. So if you remember last time, we don't have all this. Okay, your RS data from your read data 1 goes straight to ALU. Your RD goes to a multiplexer that just differentiate between the RD and the sign extended immediate. Okay, but now I have an additional layer in front. Okay, an additional multiplexer, and this multiplexer has 3 inputs: 0, 0, 0, 1, and 1, 0. Same thing here: 0, 0, 0, 1, and 1, 0. Okay, now we say that this forward is 1, 0. So 1, 0 is this line over here, and this line, if I trace it back, is actually coming out of the EX memory stage. Okay, so this is the data that is forwarded from the EX memory stage, okay, back to the IDEX stage. That means the instruction earlier. All right, so, and just to show you the next one is the memory write back hazard. So this is for 2 instructions earlier. So in the case where I have 2 instructions earlier, that means this line, okay, then I do the same thing. Okay, in the code, what I'll do is I will check whether my mem write back, because 2 instructions ago means that instruction is already in the memory write back stage. So if that RD register, the one I'm writing back to, is it the same as my current IDEX register, either RS or RT? Okay, so you can see the same pattern here. And in this case, the forward is 0, 1. Okay, and what is 0, 1? 0, 1 is the second input, which is this one. Okay, so if this line I trace back, you see that this line comes all the way to here, which is from the memory write back stage. So this is from the memory write back stage to the IDEX stage. Okay, so that is how forwarding in a sense is done, okay, actually in the hardware. Okay, we have to add additional multiplexers, okay, that will then decide based on where to forward the data from, and all this decision is made by this thing called a forward unit. So this forward unit will take in all this control signal, and then control these multiplexers to know whether do I need to do forwarding, and forwarding from where. If there's no forwarding, then I just take 0, 0, correct? That means the actual data from read data 1 and read data 2. Okay, if not, I do the appropriate forwarding. Okay, so this comes back to the point I made earlier, where why do we have the flow in a certain way? Why do I stall only at this particular stage? Okay, why? Because the hardware is really designed that way, that I will detect for this particular event. So I will only stall at this particular cycle so that the appropriate forwarding or the appropriate action can be taken. Okay, so it comes back to how the hardware is being designed. Okay, so again, this is just to show you or maybe close the loop on how this is actually done, okay, in the hardware. Okay, so it all comes back to designing all these multiplexers, control signals, and putting in all this code to detect these events. Okay, so when we look at the code, we can logically think, okay, I should do it here, I should do it there, but we need to put that into code that will translate into hardware. Okay, so that is where all these decisions come in on what should I check for and where should I check it and so on. Okay, so I hope it's a bit clearer now. Yeah, so I'll just go through some of the Slido questions that have been highlighted. For pipelining tools, like why only need 2 stalls? Why not 3? Okay, so this comes back to the idea that in this, without forwarding, we can do a write and read in the same clock cycle for the register file. Okay, so that is why I'm able to do the write back and do the read. Okay, because the write back is in the first half of the clock cycle and the read is in the second half of the clock cycle. Okay, second. Okay. Why does second end instruction stall after ID and not after IF? Okay. So again, comes back to the idea of where is the forwarding done, correct? So in this case, we know that a load word instruction, the data is available in memory. So I need to make sure that that is forwarded to the EX stage. So I stall it in the decode stage so that the moment I get the data, I can do the forwarding and my end instruction can move on to complete the EX stage. Okay, so again, it comes back to the idea of where or how the hardware is designed for forwarding. Okay, so I think this is the same question. Why the OR instruction also need to stall? Okay, so why the OR instruction need to stall is because when, like I said earlier, at any point of time, one instruction can occupy one stage in the pipeline. So my earlier instruction is already occupying the decode stage, which means that my current instruction, when it's in the IF stage, I cannot go on to the decode stage until that stage is cleared up. So that's why I have to stall until the earlier instruction moves on to the next stage. Then my current instruction will go on to the decode stage. Okay, let me see. Okay, so this why does the third instruction wait until the 5th clock cycle before starting? So it's coming back to this again. All right, so it's the same thing. All right, why? Because my earlier instruction here, okay, is already in the fetch stage and I already stalled. Okay, so I cannot put another instruction in the fetch stage until this instruction goes to the decode stage. Okay, so that is why this instruction has to wait until the earlier instruction has moved out. Okay, so most of them are quite similar. Yeah, so it's the same thing. Okay, so we move on to the control hazards. Okay, for slide, why does jump 7 and it's at 72? So this is, so when you calculate, it's always PC plus 4 plus the offset, okay, times 4. Okay, so when you add that together, 44 plus 28, then you will get, okay, 72 over here. Okay, so is the branch outcome known at the start or end of cycle 3 for branch prediction? Okay, the start. Okay, so in branch prediction, okay, in this case where we are predicting it in the second stage, in the decode stage. So by the time the decode stage is finished, we already know the decision, correct? So when we reach this end of the cycle 2, we know the decision. So from that, we have already have updated and fetched the new instruction from memory. Okay, so that would also mean that this instruction would be flush, and I would fetch the new instruction from memory if the branch prediction was wrong. Okay, so it is known at the end of that cycle, and then the next clock cycle we will fetch the new instruction. Okay, let me see. Well, lecture one's like, why do we need to check the opcode? Okay, so I think here we're talking about the slide where we have added the AND gate, okay, in the ID stage. Okay, so inside the ID stage, okay, we will also have other control hardware to check that is opcode, what is the opcode, and then the entire branch prediction, everything, and then we will generate that for the decision part. Okay, so what we sort of showed you there is just uh, the idea only, correct? There is additional hardware to also check for the control signal to make sure that we are making the branch prediction only for the branch instruction. Okay, for flushing the pipeline. All right, so this one comes back to here. Why do we say that we are going from a 3 clock cycle penalty to 1 clock cycle? Why? Because in this case, the only penalty is when I fetch an instruction and it's in the instruction fetch stage, and the earlier instruction has already made the decision in the decode stage. Okay, so the only penalty is this 1 clock cycle that I wasted if the decision is wrong. Correct. So this instruction has to be flush, and then I go to the next or fetch the correct instruction in the next clock cycle. Okay, so this idea of flush is what? This idea of flush means in a sense, you can think of it as zeroing out all the data in the pipeline. Okay, so I do not have to process whatever is in the pipeline anymore. So I zero it out, and then I can move on to the next. Okay, so let's see, pipeline performance. Okay, so this one is basically talking about okay, so in a single cycle, okay, whether it is considered whatever instruction, we still need to factor in the total time taken for the entire completion of all types of instructions. All right, so that is why we have to consider all 5 stages. So even if your instruction only has 4 stages, but since a single cycle has instruction with 5 stages, we need to factor in that could be the worst case scenario. So we use that in determining the cycle. Let me see. All right, so I think the rest of the questions are fine. Okay, so I think that brings us to the end. Yeah, so I think there was some query about the midterm question. All right, so I think Prabhu will release some of the explanation as well. So I will release explanation for this. I think that was asked in the Slido questions as well. Okay, how do we get this answer? Okay, so if you look at all of this, okay, so if you go back to your tutorial and you analyze the timing, okay, taken for all these 3 type instructions, we will see that I mean, even before analyzing, we already know that the load word is always the instruction that takes the longest time. Okay, so if you calculate this, it will give you about 1300 picoseconds, okay, to complete this instruction. Now for 1300 picoseconds, so if you take 1 over 1300 picoseconds, which is the time taken to complete one instruction, which is 1 clock cycle. All right, so this is the period. Okay, so frequency 1 by t. So 1 by t there will give me around 770 megahertz. Okay, now when I say 770 megahertz means that is the fastest I can go. I cannot go faster than this, because if I go faster than this, that means my period will get smaller. If my period gets smaller, that means I cannot complete this load word instruction. I don't have enough time to complete this load word instruction. Alright, that means the maximum speed I can go is 770. So anything lower than that is fine. Okay, so the only value that is lower than that is option A, is 100 megahertz. Okay, so that's why our answer here is A. Okay, so I think that brings us to the end of the PC related issues. You just have to bear with me for 1 more week on that. Okay. Yeah, so any questions you can stay back and ask me. If not, thank you, and I'll see you all next week for the last session.